Okay.
Just looking at that picture confirms my point that we have this talk for us. So probably people.
Thank you very much. I have two goals for this talk. One is to show you a nice visualization of the Riemann surface, and the second is to end on time. So if this works, here we go. Okay, so this talk is going to be a bit of a different style than the usual ones for this workshop. I'll talk about this idea of exponential asymptotics, and if anything, it's going to serve as an introduction to this area for those of you who haven't heard about it. Okay, so here is a mouthful definition of what exponential asymptotics is. Exponential asymptotics refers to techniques used to derive exponentially small terms, often switched on via the Stokes phenomenon. This occurs when the solution is analytically continued across Stokes lines in the complex plane. These Stokes lines emerge from singularities in the low-order terms of a divergent expansion. So there's a lot of terminology here to unpack. Let's point out a few. So we're referring to, this is the usual asymptotic approximation that you might develop for a given problem to solve some differential equation or some other system. And you're interested in exponentially small terms of this for particular reason, because it's physically important or mathematically important to satisfy boundary conditions, for instance. What happens is that often the low-order terms here have singularities in the complex plane, and this magnifies as you go on. The thing diverges often in this universal form of a factorial over power. Okay? And you'll notice that the chi here looks the same as the chi here, and that's part of the trick of doing this type of analysis. There's often a connection between the way the thing is diverging and the small, exponentially small terms you're trying to find. Okay? So our to-do list, let's give you a bit of a 10-minute introduction on this topic of exponential asymptotics. I'll explain to you how to think of exponential asymptotics for a particular application in wave structure interactions using steepest descents. And then finally, some almost philosophical discussion of where the area might be going in the future. Okay. So here's the simplest toy model that we often use when introducing this topic. If you've seen it before, it might be a bit boring, but it is really the simplest model that we've been able to find. You're interested in solving this linear differential equation when epsilon is a small number. There's a boundary condition at minus infinity. And the natural thing, if you don't want to solve it, integrate it, is that you'll just expand everything into a series expansion. Okay? So this is just the normal thing you would do. And there's nothing particularly suspicious about this series expansion. It does diverge, like this factorial over power. But at the very least, you think it behaves like epsilon over z. And so you do this numerical experiment where, okay, so our numerical experiments will start off in the complex plane, and we solve that differential equation numerically, and we simply walk from the blue dot to the red dot. And when you do so, you plot the solution, and you plot its asymptotic approximation. This is what it looks like. Okay, so the numerical solution is the solid blue, the leading order asymptotic. This is that epsilon equal to 0.3, and this is just the arc length along the curve with one of the components of that solution, the real part of the solution. So there's nothing suspicious about that. And indeed, if you take epsilon smaller, the two curves should converge. Or if you include higher order approximations, the two curves should converge. Okay? But then now you take a detour in the complex plane. You walk from this red dot to the top red dot, and you see what happens is something a bit strange. Right. Okay, that's very strange, because there's nothing in this approximation which is oscillatory. Right? So this is exponential asymptotics. So here I'm just solving this differential equation with some value beginning near 0 as I walk from this blue to the red. Right? And you can start from minus, you can just start from a large negative value and just set that to be the boundary condition. Yeah. Okay. Okay. So this will turn out to be exponentially small. Those of us who work in exponential asymptotics always have to defend ourselves when we talk about exponential smallness and why you shouldn't ignore it. You see, exponential smallness is not necessarily negligible. Right? Okay. So here's the simple explanation of why this happens. You take your differential equation and you integrate it, and you have this integral to evaluate where it's convenient later on to set a to be minus infinity so that it satisfies the boundary condition exactly, okay? And then you simply try to approximate that integral by doing the method of steepest descents. You imagine the integrand of the real part of this integrand as the height of this function. This is the integration variables real t and imaginary t. And the idea is you want to integrate from a to a point z by deforming this contour in a convenient way. When epsilon is a very small number, you're either exponentially large or exponentially small, depending on what the real part of that function is. And the deformation is simply like taking your finger and dragging everything downhill. And when you do so, you'll find that there are dominant contributions from a and from z, because everything else is exponentially small. That, in fact, just justifies the simple integration by parts. If you do integration by parts, that's exactly the asymptotic formula you derive. You take a to minus infinity, and there is your asymptotic approximation. Right? But you might see the problem now, because if z moves into the upper half plane, I have a bit of an issue. I can't deform in the usual way. I now need to include the pole. The pole adds a residue contribution, and that's your exponentially small term. Right? So that is the Stokes phenomenon. The Stokes phenomenon refers to this sudden appearance of exponentially small terms when the solution here, z, is analytically continued past the red line. When you go past the red line in the complex plane, you need to take into account the pole contribution. It's a very simple demonstration, but this kind of idea took Stokes, it occupied Stokes a number of decades of his life to understand. So just to recap, the idea is that in the z plane, when you're in the lower half plane for this differential equation, you have one asymptotic approximation. When you analytically continue this to the positive real axis, from then onwards, you have the exponentially small term that needs to be switched on. Okay? So there doesn't seem to be anything particularly magical about it in the way that we presented it, but think about what that implies. If I gave you just a differential equation, possibly a nonlinear differential equation, how could you ever known that this would happen without access to the integral? And that's kind of the magic of exponential asymptotics. Now, you might not believe that this happens. How do I prove that this happens, or prove using formal asymptotics that this happens without the integral definition? And this is the basic idea of how you do it. You'd like to show that there's a magic line on the positive real axis, the positive real z-axis, where this happens. And so you're going to zoom in near this line and rescale the problem and integrate the solution across that curve. Right? So the step one is you'll take your divergent series and optimally truncate it, and you can find out the optimal truncation point by looking at the ratio of adjacent terms, and it's of this particular form. As epsilon tends to 0, you can take more and more terms to minimize the error. And then what you do is you take the differential equation, you substitute in the optimally truncated series plus a remainder term, and you simplify everything, and that essentially gives you an equation for the remainder, a linearized equation for the remainder, which is forced by the error incurred by the asymptotic approximation because you've not satisfied it exactly. This is the crucial connection, you see, that tells you that the remainder is somehow related to the divergent series. That's why sometimes people say, oh, you're decoding the divergence. You're using that divergent behavior to tell you something about the remainder. If you know the form of the divergent term, which we do here, then you can use Stirling's approximation to change that gamma function into an exponential. And you clean things up. You put in the optimal truncation point. And what you find out is an expression like this. What you find is an expression like this, where this s here is the prefactor multiplying the remainder equation for the exponential. Notice that this is just the homogeneous solution to the left-hand side. So you could have predicted it in the first place. This equation here, if you look at this factor, is always exponentially small unless you're on the positive real axis. and there's that special line across which the Stokes line lies. You can integrate across that line in this var theta coordinate, and you find that the jump is 2 pi I. Right, and there's your Stokes phenomenon. Okay? So the magic of exponential asymptotics is explained in that algorithmic way in which you work with the differential equation, not necessarily with the integral equation. You take your linear differential equation, you truncate your series, you obtain an equation for the remainder, which is forced by the divergent terms, and then you smooth that Stokes line out, and you find those exponentials. And the key is that notice there's nothing here which really relies upon the linearity of the function. We could have replaced this with a nonlinear ODE, or PDE if you like, still substitute in an asymptotic approximation in powers of that small parameter. The difference here is the divergent form might be more complicated, but if you could find this, then in theory you would be able to find the expression of the exponential. And that, in a nutshell, is what exponential asymptotics is about. Okay? Now, throughout all of this, there are these key critical lines across which this happens. These are the Stokes lines, these Stokes phenomenon. And there's a condition on this, what we call the singulant function, this chi, or the exponential, which will tell you where the Stokes line lies. And it's the values of z such that the imaginary part of chi is equal to 0 in this particular case. There's no easy way to explain why this condition is the way it is. You can think of it in terms of a steepest descent condition. It's analogous to a steepest descent condition. Okay, and this is the end of the crash course. Exponential asymptotics provides this set of techniques to study this correspondence between divergence and exponentials. There's been a host of successes of this methodology over the many years, and you could fill a whole workshop with all the different nice applications ranging from crystal growth and Saffin-Taylor viscous fingering all the way to snaking bifurcation diagrams and on and on and on. And I've just put some pioneers and new talents in this field in the audience who've attended the workshop this week. So you can talk to them. So as a typical application that are known to some of us, if you look at a Healy-Shaw cell, which is like 2 pieces of plexiglass filled with viscous fluid, and you pump air from the top, you form these type of fingering interfaces. And the exponential asymptotics for this problem was done by people over, this problem was originally pointed out by Saffin-Taylor in 1958, but then it took another 20 years to develop the techniques to solve this problem. The idea is that there is a finger width which is selected by the PDE or by nature, in which the finger is usually half the size of the channel, but the asymptotics don't tell you that it's supposed to be a half. And you have to go to beyond all order terms. You have to find those exponentially small terms, and somehow they're crucial for satisfying the boundary conditions of that problem. And the asymptotics, the exponential asymptotics, are done in a very similar way. You take the solution of the interface, this theta is a function of the arc length, you look at the singularities in the complex plane, somehow there will be Stokes lines in that, and you look at the switching on and off of those Stokes lines. And in fact, that switching on and off is the crucial piece of information to satisfy the boundary conditions, which limits the possible values of lambda. So here's another application that I won't talk too much about. This is, if you look at traveling waterways, so this is what is sometimes known as Stokes waves, and you put a bit of surface tension into this problem, it's well known that you form these parasitic capillary ripples. Okay? And what you can do is you can then take the zero surface tension limit of the problem. This is a gravity force traveling water wave of constant form. This is known as a Stokes wave. And you can look at the analytic continuation of this solution. You'll find singularities in the complex plane that move along with the crest. And you can find Stokes lines that correspond to those singularities. And those Stokes lines govern the production of those little ripples in the limit that the surface tension parameter tends to 0. You'll notice that it's actually symmetric here, where the picture is asymmetric. And that's an interesting question of whether, if you solve potential flow for these types of configurations, do you have solutions which are asymmetric? This is an example of a problem where you try to do exponential asymptotics, but you can't actually solve for the singularities analytically. You have to solve for them numerically, and this is one of the interests of of the community, is to try to develop these methods for problems that you can't do everything with paper and pencil. Okay, so let me get to the nice application of this. I'm interested in solving Laplace's equation for flow past some solid boundary, and the parameter here is known as the Froude number. So this is low-speed flow past some body. This is a very generic problem. Okay? And you'll notice that if this Froude number, epsilon, is very small, then approximately the free surface is flat and is wave-free. And what you find out is that if you try to do your asymptotic approximations in this epsilon, these waterways will be exponentially small, generically exponentially small in this Froude number. And so the interest is, how do you predict those waterways? So over the last decade or so, we've developed many tools for doing this in two-dimensional flow. The point of this graph, so the point of this first bullet is just to note that actually we don't usually work with the potential framework. There are much more elegant ways in two dimensions, with boundary integral methods, in which the quantity of interest is often this q, a speed parameter, in some conformally mapped plane, zeta. Okay? The point of this picture was just to tell you that you could, if you don't believe me, that there are these magical Stokes lines in the Stokes phenomenon, which you might not. You could, of course, do it experimentally. You solve for this. You take epsilon smaller and smaller, and if you're very careful with your numerics and you take your numerical solution and subtract out those asymptotic approximations, you should find that the waves are switched on in a band which approaches some magical line. Right? So you could probe at this numerically if you don't want to do the asymptotics. Okay, so now I want to show you how to think of the production of these two-dimensional waves using steep descents. Okay, so the way that it's done is you have some flow over some boundary, and you'd rather map this boundary to some convenient plane, which we call the zeta plane. I don't have to tell you the details of the map, except for the fact that it sends basically this solid boundary to the left side here, and the free surface to the right side here, and it does so in a way which it flips everything around like that, you see. So essentially, downstream is now at the origin, upstream is way up there. Okay, so that's all you have to really remember when you do the steepest ascents, that if I go left to right on the free surface, I'm going right to left over there. All right, that's all you need to know about the map. The equations are essentially Bernoulli's equation on the free surface for the speed q and the angle theta, and then a boundary integral equation here, but you know certain details of the angle on the left side because you're specifying the angle is there, so you're able to write that down analytically. So this is just for flow over a step with a certain angle parameter sigma. When sigma is equal to a half, you have the rectangular step. So this is the type of problem that you can solve numerically. Okay? It's been shown, you can look at the details there, that actually you don't have to study this type of equation to study the asymptotics. In fact, all you have to do is you can, in a sense, stuff this into there and then integrate it. It's not that easy because there's a Hilbert transform, but at least for us, conceptually, you can think of the solution as being expressed as an integral involving this chi function, which is some function of the geometry. That's the key idea, that you're trying to do steep descents on this integral where the details of your flow geometry are embedded in the chi. Okay? And from that, you have the two possibilities. Firstly, if the dominant contributions are coming from the endpoints, that should redevelop your regular expansion of the differential equation, the wave-free expansion, and that you can show that's the case. Because essentially it's chi of zeta here multiplied by e to the minus chi of zeta, so you get algebraic powers in epsilon. On the other hand, if there are interior points here which contribute, like saddle points for instance, then the contribution is exponentially small. That's the basic idea. Okay, so let's do the steepest ascents. This is for flow over a rectangular step. There are two critical points in this map, the stagnation point of the step and the corner of the step. And the challenge for us is essentially to integrate from an upstream point to a downstream point and observe the switching on of these exponentially small waves. So you want to essentially take that red contour and just deform it. Okay? the paths of steep descent are indicated by the gray lines. So essentially, from this point, the path of steep descent goes around. There are two branch points. You're essentially going around in closed loops in this plane. So the more times you loop around, in a sense, the smaller the integrand. That's the basic idea. So it's like taking your finger to this red curve and just deforming it. And you keep on pulling the curve over and over in circular loops. Okay? The dominant contributions will come from the two endpoints, because everything else is smaller in the integrand. And that is essentially just your regular perturbative series. On the other hand, you notice that if the downstream point moves sufficiently close, then there's a bit of an issue. Because actually, the downstream point has steep descent paths that look like that. The upstream point has steep descent paths that look like that. But there's no way to join the two that easily. Okay? And so, in essence, the penalty you have for going from the outside to the inside of the pink curves are those exponentially small terms. Okay? Whenever I explain that, and so this pink curve is the Stokes line. So if you projected this pink curve into the physical plane, it would tell you the location where the waves are switched on. Whenever I explain this, people say, it's even not that clear how you get that contribution. And I say, well, you can look at the paper and look at the deformation in the paper, and we explain how that's the case. If in a sense, it's easier not to do steep descents. You kind of want to rescale around that point and then write down the contour integrals. Okay, so that's essentially what these pictures are about. They're essentially about the idea of associating geometries, geometrical flows past objects, and trying to understand the production of water waves as you deform the objects. You're essentially changing the Riemann surface and changing the paths of steepest descent. And that gives you a very powerful tool to study that correspondence. Okay. I have to be a bit strategic. I've got 5 minutes left, and I definitely don't want to go over time. So where is this all going? I would say the field is going in two directions, or at least those of us who are working together are going in two directions. The first is to extend these type of methods to problems in which you cannot write down the conformal map analytically. Right? So this is quite interesting. You would think, for instance, that if you take a step and you deform it very slightly, then you can still do the analysis, and the waterways wouldn't have changed very much. But that's not quite so clear if you think of the method of steepest descent. It depends quite crucially upon locating key points in the topology of the complex function and doing that deformation process. Can you take these methods and then stuff in things like rational approximants? Rather than writing down the conformal maps, you input rational approximants or Pade approximants for your conformal maps, and that would tell you, and then you crank the handle, it would tell you the exponential small waves that arise. The last type of thing, I actually have about 10 more slides to do, but I'm going to actually end it here because it would be the biggest offense to go over at 5 p.m. So I'll tell you about this direction that we want to go in. In essence, if you look at all of exponential asymptotics over the last really 20 years, the vast majority of it has been devoted to two-dimensional problems. Why? Because it's so steep in complex variable theory that 2 dimensions is just the natural setting for complex variables. We don't have that many applications of exponential asymptotics for higher dimensional problems, 3-dimensional problems. And yet, intuitively, you would expect the same type of situation to arise in higher dimensions. You know the water waves will be exponentially small, right? Or at least you should be convinced of that fact. And so by the same type of mechanism, you would expect that there is a location in the physical flow, here flow past some complicated geometry, such that if you were to do your numerics very carefully, like this experiment, you take epsilon smaller and smaller, you would find that key location in the fluid where the waves are switched on. How do you find that location? So this is the idea of a Stokes surface, a multidimensional generalization of a Stokes line. I'll say that It's been done by Lustre and Chapman. They looked at flow past a point source for a linear point source. You can do it in that case, find these critical lines, but it's not clear how you would generalize these techniques to a particular geometry. What we would really want is for you to just draw out any geometry. We put this into our computer, and then we crank the handle. It would tell you this special surface. And there are some ways that we've been developing over the last year to do this, but I don't have enough time to talk about it. Thank you very much.
Questions, comments?
You mentioned the recent work to do with the quantitative way of developing all of these data. Were you able to derive from that? Is there any hope of deriving some kind of statistics compared to the measurements where there's a real mystery about the skewness of this distribution through waves on the ocean?
Can you say a bit more on what you mean by skewness?
So if you take a PDF of some satellites or some airborne measurements of ocean sea surface slope, there is a well-known question as to what sets the skewness as in the third moment of the PDF.
I see. So we're much more fundamental in this. Our calculations in 2D, and we're asking a much more fundamental question, which is if you take just regular inviscid flow, Laplace equation with Bernoulli's equation, surface tension, and gravity, can you even get these type of parasitic capillary waves? And the answer seems to be no. The answer seems to be that you need additional physical mechanisms even to generate solutions of that problem. So you need time dependence.
It's even a lab. There was a question as to whether they're treated by science.
Yeah. So the question of what model you even need for parasitic capillary waves is an open question.
So, in cases where you have a boundary interpolation, whether it is 2D or 3D, a strategy that can be followed is to complexify the parameter and locate in the parameter plane the nearest. You have a manifold, as you mentioned. You have a manifold. What's the nearest location of the singularity manifold?
Yeah.
And that's actually related to the Crystal-Seeger procedure. Once you locate the nearest location of the manifold, so what you do is you change variables so that that manifold is straightened.
Yeah.
And that's the way to go, actually.
Yeah, it's true. So I think Sally's point is that, as the connection to this is we have these very complicated surfaces where you have to do steepest descents. And it's an interesting question of can you do a map so that it's much more simple? And I think in a sense that's the idea of Borel summation, that you do a canonical map where the points are, the branch cuts all go in one direction, and your integration path is much more simple. I don't know if you do that type of map for this, whether it cleans up the analysis. And it's also an interesting question of can you do that in higher dimensions as well?
Yeah, and
One final question before we close this lecture.
Oh, can I meant to advertise the next I&I program, which might be a good way of ending the talk. Just promote, there's a program in 2021, January to June 2021, on resurgence, which is one of the areas that is connected to exponential asymptotics. So in a sense, this is sort of a 10-year follow-up to a previous program, more than 10 years, in 1995, I think, on exponential asymptotics. So.
So there you go. Then the final word of thanks to everyone who participated in these giving such wonderful talks as we just saw, or just asked good questions.